In this video, we'll discuss the backpropagation of an AI transformer in C++. In the few previous videos, we have discussed the transformer architecture and the implementations of the encoder and decoder in C++. This figure shows the transformer architecture. We discussed this before. This is the encoder. It repeats for 6 times, and this is the decoder. It also repeats for 6 times. So that means we have 6 layers of encoder, or 6 decoder layers. Okay. And the output, the final output of the encoder is E, and this will be input to the coarse multi-head attention of the decoder. The external input is X, and the output here is X1, okay? And then the output here is X2, and we can call the output here to be X3 or Y, and then it goes to linear and softmax, okay, at the last decoder layer. Okay. So actually, if you expand this, so these encoder layers, it looks like this. So we have this input, okay, and this is encoder 1. Okay. So the output of this goes to the second encoder, and the second encoder output goes to the third encoder, okay, and so on. And the final output, the output of the decoder 6 is E. Okay. And this E goes to all the multi-head attentions of the decoders. Okay. So it looks like this. So these are encoder layers, decoder layers. So decoder 1, the output goes to decoder 2, and so on. And the final output is E. So E will go to each of the decoders. Okay, decoder 1, decoder 2, decoder 3, and blah blah, decoder 6. And so these are done in parallel. This E goes to each of these decoder, but the output of decoder 1 will go to the output, the input of decoder 2, and so on. The output here means the X3 here. Okay, it's only the last output, output of layer 6, will go to this linear and softmax. So that's the basic architecture of an AI transformer. And now let's see how we do backpropagations. Let's have a brief review of the forward pass of a decoder. We use index 1 to refer to the first multi-head block, and index 2 to refer to the second multi-head attention block. Okay. And we use these notations. X is the input to the decoder, okay, or to the first multi-head attention. And X1, okay, so this is X1, is after this first block, okay, and X2 is after the second block, or the cross attention block. Okay. And the final output is Y, or X3, it's after the feedforward network, okay, the output here. And E is the encoder output, or the input to the cross multi-head attention. Okay. And these are the equations for these blocks for the masked multi-head attention or the first attention block. Okay, so we calculate Q1, K1, V1 from the input X, okay, using the weight matrices WQ. Q means QR, okay, WK, K is key, and WV value. Yeah, and the index 1 here refers to the first block. Okay, it is the masked self-attention here. Okay. And the output, okay, after the calculations with input X, then we obtain the output H1. Okay. And after the and norm, then we get X1 here. Okay. The Ln here means layer norm, layer norm of X, okay, plus H1. Okay. And the second block, the cross attention block. Okay. So we get Q2, K2, V2 from the WQ, WK, and WV. But we have different inputs. Okay, Q2 is from X1 here. K2 and V2 are from E, okay, E here. Okay. So we get this, and we after the math, the softmax, okay, and matrix multiplication with these inputs X1E, we get H2. Okay, the output here is H2, and then we add it to the residue X1 and to the layer long, so we get output X2 here, okay. And then this X2 will go into the feedforward network. So we calculate F1 to be F, the product of X2 W1. The lower F here means the activation function. We can use the redo activation function. And F2 is F1 times the weight matrix W2. And Y is the output after the layer long. Okay. Layer long of X2 plus F2, as shown in this diagram. So this output is Y. Okay. Backpropagation means to make use of the difference between the outputs of the transformer and the targeted values to adjust the ways of the transformer. The softmax function here will give us the probabilities from the final output of the decoder. So this is the softmax formula. So it generates probabilities. So here NV is the vocabulary size, and NT is the number of tokens in the targeted sequence, and K is the true token index, and this is the entropy loss L. So you can see that if we have a certain prediction, the probability could be 1, okay, and log 1 is 0, so the loss is 0. Okay. On the other hand, if the probability is very small, then it generates a large negative log value, and negative will get a positive large values. Now, this is a general method. It's not exact, but it just tells us the general idea how the backpropagation works. Now, this is the forward computation. Y equals the input X times the weight W. Okay. Then the gradient, partial L, partial W, is given by this formula, the transpose of X times the gradient of L with respect to y. Okay. If we can obtain this dl dw, then we can calculate the delta w, which is equal to a small constant eta times this gradient. Okay, and then we put a negative sign here. Okay, and then we update the weight by adding this delta w to the original weight. Okay, and then we compute the input gradient, which is given by partial L partial x, which is equal to partial L partial y, okay, from here, okay, times Wt, okay, the transpose of the weights. Okay. And this partial L partial x will become the partial L partial y of the next state. For convenience of speaking, I will refer to the partial symbol as d. Okay, so this is dl dx. Okay. Now, to start, we need a dl dy. So this is the starting gradient, dl dy, which is equal to p minus t. So p is obtained by this formula, the softmax, okay? And T is the target matrix, okay, given by this formula. Okay? So Tij is 1. If J is equal to K, K is the actual token index. Okay? Otherwise it's 0. Okay? Now in this formula, we actually don't need L to compute dl dy. Okay? So just like the speed. Calculating the speed, we may not need the distance to calculate the speed. Okay? So once we get the dl dy, we can compute the gradient with respect to the weights. Okay. Now this is a simple program, okay, that compute dl dy from the p and t. Okay. So the input matrix is our y, okay, or the lodges. Okay, the dimension is nt times mv, and target, okay, is of size nt. Okay. So we calculate nt and mv from the matrix y, okay, and matrix t, okay, is nt times mv actually, okay. And it starts with all 0. Okay, so most of these are 0. Okay, we start with all 0, okay. And we let the dl dy to be t. That means we set them to have the same dimensions. Okay. And we compute the softmax probabilities. We discussed this before. Softmax. We discussed that in the video about multilayer perceptron. And now this is a one hot target building. Okay, so K equals target I, okay, and this K will be 1. Okay, all others will be 0. Okay, I mean this T ik will be 1, others will be 0. Okay. And then we compute the gradient, okay, dl dy, which is p minus t. Okay. So dl dy ij is pj minus tij. Okay, this formula. Okay. And then we turn dl dy. Now actually we can shorten this method by using a code like this. So we start with dl dy equals pj, okay, or equals pj, and then because there's only one entry, that will be 0. So we just dl dy I target I, okay, this entry, okay, we subtract 1 from it because the target is 1, okay, for this case, okay. Now let's and then we return dl dy, okay. Now this is a main program for testing this routine. Now let's try this. We've copied this program to this file, okay, dl dy, okay, and now we can compile that. We have also copied the utility programs that contain the softmax function. So we can say gpurpose -o dl dy and link this with the utility, okay, and this prints out the dl dy matrix, okay. Now we can also do this without the T matrix. We can comment this out, for example. Comment this out from here to here and uncomment this. Now let's recompile this. So it also recompiles, and we get the same results. Okay, so either method is fine. The later is more efficient. So using this dl dy, we can calculate the weight gradients, and from the weight gradients we calculate the delta W and use it to update the corresponding weights. And we can also calculate the gradient with respect to the input and pass it to the next stage. Okay. Now, these are the weights or parameters that we need to update. We need to update the attention projection weights, WQ, WK, WV, WO, and the feed-forward weights, W1, W2, and also the layer long parameters, gamma, beta. We need to do that for each decoder layer and each encoder layer independently. And the backward pass start from the final layer long. We assume that dl dy is the gradient from the layer above. Okay? So from the very beginning, we get the dl dy from this formula. Okay? And for simplicity, we ignore the bias. Okay? So we start from the final layer long, that's the output. Okay? So in this diagram, okay, it is this part. Okay? And so F1 is given by this, F2 is given by this, and then the final output is the layer long of the sum of X2 and F2. F2 is the output from here. Okay. So we start from here, okay, and we find the gradient with respect to F2, the feedforward network. Using the chain rule, this is given by dl dy times dlm means the layer long, df2, and dl dx2. As the input is dl dy times dln dx2 plus dl df2. We'll expand dln dx2 below. Next is the feedforward network. We need to calculate the output gradient in order to calculate the weight gradients. Now remember, our output is F2, which is equal to F1 W2. Okay, so this guy here. We make simplifications by assuming that dl df2 is equal to dl dy. So it means from here, dl df2 originally is equal to dl dy times this part. So we ignore this part here. And by making this assumption, we know dl df2, and from there we can calculate dl dw2, which is equal to f1 transpose dl df2, because of this formula. And dl df1 is equal to dl df2 w2 transpose, and dl dz1 is equal to dl df1 element-wise multiplication f dash x2 w1. The z1 here is actually this argument x2 times w1, and so this is the derivative of the function with respect to the argument. And suppose we use the redo activation function, then the fc is equal to maximum of 0 and c. And the derivative of it is given by this formula. It is equal to 1 if z is larger than 0, and it is 0 if z is smaller than or equal to 0. So this is known. And dl dz, or the gradient with respect to the argument, dl dz, the c1 here, is equal to dl df1 element-wise multiplication 1 z larger than 0. This formula can be written like this. The 1 here means a matrix of 1 when z is larger than 0. Otherwise, the elements are 0. Okay. A shorthand writing of this. With this known, then we can calculate dl dw1, which is equal to the input x2 transpose times the dl dc1. And finally, the dl dx2, the gradient with respect to the input is dl dz1 w1 transpose. And if we add the residual contribution, then dl dx2 is the dl dy plus this part. Next is the cross multi-head attention. It is this block here as inputs x1 and input e. So the QE is from x, and key and values are from X. We can simplify the process by assuming dl dx2 is equal to dl dx2. That means we ignore the and norm effect. So suppose A2 is equal to the softmax of this product times V2, then X2 is equal to A2 WO, the output matrix. Okay. Index 2 here means we refer to the coarse multi-head attention. So because the equations involve the softmax function, so we need to calculate its derivative. Suppose P2 is the output of the softmax of S2. S2 is the argument, okay, this part, and A2 is equal to this P2 times V2. So the probability gradient can be calculated as we mentioned earlier. With this given, the derivative of L with respect to S2 is given by this equation. I'll elaborate this more below. With this calculated, we could calculate dl dA2. Suppose we have found dl dx2. So this is equal to dl dx2 times WO transpose. And dl dWO is equal to the transpose of A2 times the dl dx2. With dl dWO given, then we can update WO. For the attention output, dl dV2 and dl dP2 are given by these formulas. So dl dA2 is known, and we can calculate from that. We can calculate the outputs, the gradient, the gradient's output. And for the scores, so S2 is equal to a softmax argument. Then dl dQ2 is given by this formula. dl dK2 is given by this. And the projection weight gradients could be calculated using these formulas. Like dl dWQ is x1, the input transpose, dl dQ2, and dl dWK is E transpose dl dK2. Remember, the key is generated from E, and Q is generated from x1. And dl dWV is E transpose dl dV2. And with this gradients of weights known, then we can update the weights as discussed before. And the gradients can, two inputs can be calculated. dl dx1 would be equal to dl dQ2, okay, WQ transpose, and dl dE is equal to dl dK2 WK transpose plus dl dV2 WV transpose. Now, the next is the masked attention. the equations are very similar. So the only thing is that mass simply enforces dl ds1 ij is equal to 0 when the mass block applies, or when the mass blocks attention. We can simplify again this by assuming dl dx1 equals dl dx1. We have similar equations as cross MHA with index 2 replaced by index 1. And here the final gradient to previous decoder layer is dl dx equals dl dq1 wq transpose and dl dk1 wk transpose plus dl dv1 wv transpose. And this dl dx becomes the dl dy of the layer below. This is because in our notation, x is the input and y is output. So the output of the lower layer becomes the input of the upper layer or upper block. And in backpropagation, we go in the reverse direction. So this dl dx becomes the dl dy of the block below. In implementing the backpropagations, we need to pay attention to the dimensions of the variables. Suppose we let nt to be the number of tokens in target sequence, n as the number of tokens in source sequence, d model the model dimension, nv the vocabulary size. For simplicity, we could assume the vocabulary size for the target and the source are the same. With this assumption, the decoder input x has dimensions nt times d model, and decoder output y the dimension nt times mv. The encoder output E, which is the input to the cross attention block, is ns times d model. And the linear ways, W is d model times nv. The logic C, x times W, which is nt times mv. The probabilities P is nt times mv. The target matrix we mentioned, T, is nt times mv. The loss L is just a scalar, the output of the softmax model. And gamma beta 1 times d model. So they are basically column vectors. And the gradient dl d beta is 1 times d model. Well, the same for dl d gamma. The gradient loss with respect to output, dl dy, is nt times mv. And the gradient loss with respect to ways, dl dw, is d model times mv. The gradient loss with respect to input, or dl dx, is nt times d model. Now we can discuss the backpropagation implementations. We start with and norm, because the final model is and norm over here, and the one below is feedforward. We also have and norm here and norm here. Now we discussed a norm before. These are equations for the forward computation. If we have an input vector xi with m values, then the mean is given by the average of these values, and the variance sigma I squared is the average of the sum of the deviation square. And normalization means we calculate the deviation of each element from the mean divided by the variance. But for stability, we add a small constant to sigma I squared and then take the square root. And the final output would be gamma times this normalized value plus another constant, beta, not constant. Actually, gamma and beta are learnable scale and shift parameters. In the backpop process, we let y to be lnc. Ln means layer long, and c is the argument. C is already the residue sum. So y basically is the yij here, okay, the output. And we let c hat to be the normalized c. And that's this xij values here, okay, c hat. Now suppose we let gy to be dl dy, the gradient with respect to y. And remember, we could calculate dl dy from at the beginning using this formula from the laws calculated from here. Okay, so we calculate the dl dy for this, and then after that we calculate the dl dx, which will be the dl dy for the stage below. So dl dy is given, and dl dc hat is given by gy times gamma. This is element-wise multiplication. And dl d beta is 1 transpose times gy. This is matrix multiplication. So 1 is a column vector, so 1 transpose becomes a row vector, and so it times the gy. That means we sum over the columns, sum over a column of the gy elements to give one value of dl d beta. So to iterate, if we have d model columns, then we have d model values, okay, for this. So there's what the dimension of dl d beta 1 times d model. Similarly, dl d gamma is 1 transpose times gy element-wise multiplication with c hat. Okay. So again, this becomes a row vector. Okay. It's sum over the columns, columns of this product. Okay. And backpop input, which will be used for the next stage. Okay. dl dc hat, the same as dl dc, is equal to 1 over sigma times gc minus the mean of gc hat minus c hat, element-wise multiplication with the mean of this. Yeah. So these are the equations, and this is the implementation. Sorry, here I mean we sum over the rows of a column to give one element of DL D gamma. So there are totally D model columns. So that means that we have D model DL D gamma values. This is the implementation. Okay, we declare the class anom with vector gamma, the size is D model, beta, size D model, and matrix C hat, the normalized values, okay, is NT times D model, the mean per row, the variance per row, and the small value EPS epsilon, and this is constructor with input parameters D model. So the gamma values are set to 1, beta value is 0, epsilon is 10 to the negative 5. We assume that we have implemented a forward computation, so we discussed this before in a video about multi-perception, multi-layer perception. So we have a C hat, mean, and variance. These have been calculated. So in the backprop routine, the input parameters are x, dl, dy, and eta. So nt is x size, mm is d model. It is x0 size. And we declare the matrix DLDC with dimensions nt and m is the D model, and fill that with value 0. And DL, D gamma, dimension D model, fill with value 0. The same for DL, D beta. And so we compute DL, D gamma, and DL, D beta using these formulas. So DL, D beta, we have to sum over the rows for all the columns. Okay. So J specifies different columns. Okay, and we have to sum over I. That's the row, different rows. Okay. The same for DL, D gamma, except that we need to multiply this by C hat. Okay, element-wise multiplication. Okay. And again, this one transpose vector is to do this sum. Okay. And then we update the parameters. The standard method with decrement by eta times the DL D gamma or DL D beta. So this is standard method. Okay. Something like this. Okay. And after that, we have to calculate this DLDC for the next state. And so we let inverse sigma to be 1 over square root the variance plus the epsilon. So this part, so that we don't need to write the square root all the time. So this is that part, okay. And the LDC hat is dl dy times the gamma. Okay, here, dl gy is dl dy. Okay, this formula, dldc hat. Okay, and then to calculate this, we need to calculate the mean. To calculate the mean, we need to sum over some values. So we declare this sum dl dc hat to be 0, and also we need the mean of this part. So we call it dl dc hat c hat. We calculate sum first, and then we get the mean. So the sum is to sum over all these dldc hat values, and this part we sum over this times this, and then the mean is given by this sum over m, over m. So this mean and this mean, over m, okay. And we multiply this by c hat, and also inverse sigma. So this is a strict implementation, nothing tricky. 1 divided by m is to take the mean. Okay, the mean of this and this, okay, that's the mean. And after that, we return the dldc to be used for the next stage. The block below the last add and norm is the feedforward network. The implementation of the backpropagation of this block is straightforward. Involve two matrices W1, W2, and we need the D model and DFF. DFF is the dimension of the feedforward network. And as discussed before, these are the forward computation equations. F1 is F, the activation function of the product of X2, W1. So we can implement this like this. The C is this argument X2 times W1. And F1 is the output of the activation function of C. Okay. And F2 is the product of F1, W2. Okay. And we return F2. Now this is the backprop routine. So the input X is given. Also the dl dy is given. We assume that it is equal to dl df2, and also eta is the learning constant. So for W2, we use this formula. dl dw2 is equal to F transpose times the dl df2. Is straightforward. So we calculate transpose first and then use matrix multiplication to find dl dw2. And dl df1 is given by this. dl df2 times w2 transpose. So we use this function to calculate w2 transpose. And final dl dc1 is given by the C, we call it F derivative of C. It is straightforward. I think it is given by this formula. Okay, and so we start with DLDC1, and DLDC1 is DLDF1, element-wise multiplication, circle dot, of this FDC, the derivative of this argument, given by this. And then for W1, so DLDW1 is say this X2 transpose times the DLDC1. So DLDW1 is matrix X transpose times DLDC1. Okay, the X is our X2 here, the input, the generic name. And then dl dx is equal to dl dc1 times w1 transpose. Okay, again, we use this matrix map to do it. And then we update the weights, okay, as we discussed before, very straightforward. And we return the gradient with respect to the input, so that's dl dx. This dl dx becomes the dl dy of the next stage. Lastly, let's discuss the implementation of the backpropagation of multi-head attention. Here we need a function to update the weights. We call it the weight update. The weight update is given by these formulas. So delta wij is minus eta dl dwij, and then we add delta wij to the original wij to get the new weight. Okay. And so this w is this w, dl dw is this dl dw, eta is this eta, and so wij decremented by eta times dl dwij, basically this formula. And here's the class for multi-head attention. It has primary members, D model, which is the dimension, n heads, the number of heads, dk is the dimension per head. And these are the weight matrices, WQ, WK, WLV, WO. And so in the constructor, we set dk to d model divided by n heads. And so this is the interface for the forward compute attention that returns the attention of the block, okay, with or without mass, okay, with inputs xq, xk, x3, okay, which could be say x1 or e. Now, these are the routines for the backpropagation implementation. We need a function to implement the softmax derivative that we mentioned earlier. Okay, so this this formula. Now this formula could be simplified to a form like this, easier to implement. So it is given by this formula. dl/ds is p circle dot this block, okay. dl/dp minus row sum of p circle dot dl/dp. The circle dot here is the head-mad multiplication. That means element-wise multiplication. And the row sum here produces a column vector with dimension nt times 1. And then broadcast across the columns. That means each column will use this column vector is subtracted from dl/dp. That's what this formula means. So this row sum is basically the dot product of two vectors. And this shows its implementation. So nt is p dot size. P is this P, the probability matrix. dl/dp is this dl/dp. These are input parameters. So we calculate nt and ns and declare the dl/ds with these dimensions nt and s, and initialized all the elements to have values 0. And here we calculate the dot product of two vectors. So it is pij times dl/dp ij for sum over the j, two vectors. Because this is a element-wise multiplication. So that's what this means. And this dot will be used by all columns. Actually, I mean the dl/ds. This is a typo error, not da. So that means dl/ds ij is pij times dl/dp ij minus dot. dl/dp, this guy minus this dot. This dot is this row sum, and we return dl/ds. So this is the implementation of the softmax derivative, and this will be used in our backprop. So this is a function backprop with these inputs xq, xk, xv, dl, dh, the eta, and mask. Now let's copy this to a file so that we can refer to the formulas we discussed earlier easier. Here, copy this. I've just copied this code to this file t.cpp. So this is the code we were discussing, and this is the backprop function with these inputs xq, xk, xv, dl, dh, eta, and the mask, which could be true or false. Now let's reference the formulas we discussed earlier about multi-head attention. So these are the formulas for coarse multi-head attention. Is similar for the masked multi-head attention. So for this, the mask is false. For the other mask is true in our implementation. Okay. Now the QKV here are obtained by projecting the inputs from the corresponding weight matrices. Okay. So these are inputs, and inputs in these formulas for the coarse multi-head is X1 EE. Okay. So we obtain QKV from these formulas, and from this product we obtain the A value. So we calculate S, this argument, the Q times K transpose, and then scale it. It's 1 over square root D, and we use this utility function scale met to multiply this S by the scale. Okay, this 1 over square root D. Okay. So the S is this argument, and P is this output softmax of S. And of course it could be with or without mask. Okay, this is the P, the probability. And this P times V give us A. Okay, so the P A is the P times V. And the LDA and the LDWO are given by these two formulas. Okay. So the LDA is DLDH times WO transpose, or transpose of WO. And the LDWO is A transpose times DLDH. And for the attention output, the LDV is P transpose times the LDA. And the LDS is given by the softmax derivative that we discussed before. The LDP, P are the inputs for this function. Okay, so this gives us the LDS. And then for the output, we have the DLDQ equals the DLDS times K, and we need to multiply it by this constant. Okay, that's our scale. And the LDK is given by the DLDS times Q. Again, we do the scale. Then finally, the weight gradients. So DLDWQ is the transpose of XQ. XQ is X1 here. DLDQ. And DLDWK is the transpose of XK. XK is E here. Okay. And DLDK. And DLDWV is transpose of XV. XV is the E here, okay, times DLDV. Okay. And we could also calculate the input gradients. Okay. DLDQ corresponding to our dl dx1. X1 is the input. That correspond to our xq. And it is equal to dl dq times the transpose of wq. And the same for the other two parameters. Xk is our e, xv is also our e, are given by the dl dk times wk transpose, and also the dl dxv is also dl de here. Is given by dl dv, times the transpose of wv. And with the weight gradients known, we can update the weights easily. You're calling this function update weight with value of eta. And we returned dl dxq for the usage of the block below, or the previous block. So dl dxq is our dl dx1. X1 is our input in the discussion here. So this wraps up our discussion on this topic. It's been a long video. Thank you for your patience of watching. I hope you could learn something from this video, and I would see you in the next video. Thank you for watching. Bye-bye.